Okay, good morning, everyone. And today's topic is going to be sequential circuits. So, any questions from previous class or anything that you want to ask? Usually, I will have any another doubt clearing session first, and then I'll move to the topic. So, is there any questions, something, or any kind of queries that I can answer regarding the previous class? Okay, all right. We'll get started on the sequential circuits. Okay, so last week we have talked about combinational circuits. Okay, let's do a quick recap. So basic build logic blocks. Okay, we have gone through the basic gates. Okay, so all the kind of gates and where they would be used and etc. And we also have gone through the universal gates. So in books you would have seen kind of those you might have seen like kind of only mux and no, NAND and NOR. Mux you wouldn't have seen anywhere. So I also have showed you how do we come up with a logic, whatever the logic using mux also. The reason is because in industry you will have a muxes in your design as a spare gate, and you would be using them using those muxes to implement any logic if required. Okay, and we have just gone through basics of Boolean algebra and like what is the right way of designing a circuit. The first thing is always any kind of problems. The first thing you need to do is bring your truth table and then solve your the output, probably come up with an optimized equation, and then you have to draw the circuit. And we also have talked about different circuits and the meaning of optimizations, say in terms of power, performance, area. Okay, so we talked about like kind of basics of how many transistors that you should have, say among, if you look at how many transistors would be there in this circuit, and how many transistors would be there in this circuit, and how many transistors would be there in this circuit. So, and what is the total time that is going to take from input to output, and all of that, right? And we have done some, we do, we also have spent some time on working through this De Morgan's theorem, because this is what it would be used when you are trying to implement uh, the circuit using only NAND configuration, or say NOR kind of configurations. Okay, so logic implementation using NAND, we spent some time and we also solved some problems, and we also have gone through Karnaugh maps. So, and we also have discussed like kind of manually it is not possible to go beyond five variables if you are doing it manually. But if you guys look at the current industry is using a lot of tools and the algorithms, so they are capable of optimizing, see, even with the inputs of 10,000 plus. Okay, And this basics of half adder, full adder. I think I did not work on this. I might have left it to you guys. So hope you guys would have gone through it. And multiplexer, yes, we have gone through this mux. Okay, and we tried implementing few problems basically. So how do you implement your logics using mux? And we also have worked on or probably solved a problem implementing this whole combination logic using mux. Okay, so these are all the topics, and these are all the topics that I gave as a homework. Okay, and as a part of this, I think I might have given a couple of more homeworks also. So unfortunately, I did not hear from anyone regarding those homeworks. Okay, all right. So from next week onwards, so from this week onwards, I would expect you to work on those homeworks and send it back. So I want you to write it in a A4 sheet or probably a long notebook and write it for off page or whatever it is. I don't want you to write essays. So just a short answer, short and crisp answer, say in terms of bullet points or anything which is going to help you to prepare your interview, prepare for your interviews. Okay. Okay. So today's topic is basically sequential circuits. So what is sequential circuits? So we have seen combinational circuit and which is purely depending on your inputs. Okay, we don't rely on only inputs in case of sequential circuit. So we do rely on, probably we do look at your previous state or say previous output and etc. So that is something that we call it a storage. Okay, so if you look at here, so combination circuit plus storage element. Okay, and output depends not just on present inputs and but on the past sequence of inputs. Okay, so that is the beauty of sequential circuit. So if you look at, you might have heard about something called flip flops. Okay, and there is something called latches. So these two are the types that two types of sequential circuits are probably elements that you can say. Okay, okay. So I hope you guys have a pen and paper. We would be solving a couple of problems. Okay. Uh, so what is clock circuit? Why? What is clock signal? Why do you need clock signal? So all the sequential circuits, right, or elements, they would be operating with uh, clock. Nothing would be operating, without clock. They would be kind of, ideal. So now, if you look at this particular thing, say from this is your rising edge. Say if you look at, we usually draw a clock something like this. Okay, right? But it will not be exactly like this in the real world. You need to account the rise transition. So any signal, right? So from 0 to 1, if it is moving, there is a finite amount of time that takes, and then from there again say 1 to 0 again, it takes amount of time. Okay, so we always draw it something like this. Now, what is called a cycle? Now, if you look at from this to this, it is called one clock cycle. It's basically one clock cycle. Okay. Now, when you say one clock cycle, that means it is basically clock meaning what? It basically contains both on and off. Okay. So, if you look at in this scenario, your duty cycle. So, do you guys remember something called duty cycle? It is called T on, by T on plus T off. So this particular guy is something like kind of say 50% duty cycle clock. 50% duty cycle. Now, if you look at now if you look at this would be say something like kind of 25% duty cycle. Okay, it may be 25% of duty cycle. Now, in industry, just for your information, we always prefer 50%. We don't rely on this 25% and all. Okay, we always prefer 50% duty cycle. So any clock that you take in industry, it would be something like this. Now, anything that you have something like this kind of 25% or any of this, they all may be part of some control logic. Okay, you may not have 25% duty cycle clocks in the industry. Okay, so you can note down this question. Why don't we prefer this kind of clock in industry or in our designs? Okay, so the hint is I want you to go back and read something called full cycle path, okay, and half cycle path. So if you read about these two, you would get the answer. Okay. Okay. Now, so I hope you guys haven't got an idea of clock cycle. And then, as I said, this is going to be your rise transition, and this is your regular, the logic one. Okay, and this is going to be your, the fall transition. Okay. Now you might wonder, do we really bother this rise time and fall time and all? Yes, we do. So any signal that is going from, okay, so there is another homework for you. Say this is your signal, okay. So case one, okay, case two, so this is case two, and this is case three. So among these three, which one would you prefer? Okay, among these three, which one would you prefer? So if you look at, say this transition time, okay, this is a homework. I want you guys to go back and spend some time on it so that like you guys would be able to understand this. So now the amount of time it's basically from here to here. Say in this case 100 PS transition, okay, and say this is 300 PS transition, and say this is 200 PS transition. Okay. Now, which one among this you prefer and the reason? I need you to see these are all some things which will help you to get to know more on the transistor levels. Okay, so these are all the things that industry actually looks at from a the hiring perspective. Okay. Okay, moving on. So clock signal. So one thing is clock period. This clock period is nothing but your cycle. Okay, and next thing is basically your clock frequency. So I'm sure everyone would have gone through the basic equation of say f equal to 1 by t. Okay, it's something that you would have gone through during your college days, or say during your digital uh, circuit subject time. Okay, now I have a few things over here. Okay, now what is going to be, so t is equal to 1 by f. Now what is going to be my clock period? So let's say, so I'm sure everyone would have gone through or probably would have known something called frequency. So when you are buying phone, what is going to be your frequency? It is going to be minimum 2 gig. Okay, this CPU your CPU frequency, not the whole chip frequency. Okay, now say 2 gig or 2.4 gig and etc. Okay, now if you look at, say in your design, okay, so you may have blocks. Say for example, so your full chip would be divided into a smaller ones like this, which is known as blocks. Okay, so this is kind of your full chip. Okay, now when I say frequency, assume this is your CPU. Okay, now say this is your PLL, say this is your GPU, say this is your DDR, say this is your PCIe, okay, say this is your modem, and etc. Now, if you look at, do you really think the whole chip would be operating at 2 gig? The answer is no. So, only CPU portion would be operating at 2 gig. All the other blocks would be operating at, say, kind of anywhere between 500 to 800 megahertz, not beyond that. So, if you think, oh no, the whole chip would be operating at 2 gig, say for example in a simple mobile chip, you're wrong. So only CPU would be operating at 2 gig, but the other things and all would be operating at a lesser frequency, because CPU is the one who it would be doing a lot of arithmetic operations and support all these functions, right? So CPU would be always on a higher frequency, whereas the other logics would be on a lower frequency. So if you get an opportunity to work on say Qualcomm chips or say MediaTek, okay, you would be able to figure out, or probably you would get to know whatever that I'm telling. Yes, I have done CPU for both of these companies, and the other guys who other than CPU guys, they all will be working with 500 to 800, and I used to curse myself, why am I struggling with 2 gig, but those guys are enjoying the life. So that is how I got to know. Okay, now let's quickly, okay, what is going to be the answer for your first thing? Let's go from bottom. Okay, so 10 megahertz, so how do you convert it into the clock period? So because the reason is, this kind of questions would be definitely present in your written test. Okay, you can ping your answer. So 10 megahertz, what is your clock period? The answer is, the formula is I have given here. You guys can just ping me your answer. Okay, just ping me the answer, please. Okay. So first case is basically 10 megahertz. Okay. Um, so in the interest of time, let me just do a math in front of you. Okay. So mega meaning 10 to the power 6. Okay. Now if you solve this, say 1 by 10 into 10 to the power minus 6, which is going to be kind of, say 1 by 10 is zero point 0.1. This 10 to the power is, so basically kilo, 10 to the power 3 is micro, and 10 to the power 12 is nano, and pico is going to be 10 to the power 12. So zero point 0.1 microseconds. Now if you convert this into ns, it is going to be 100 ns. The answer for this is basically 100 ns. Okay, now what about this second one? Because if you take one more thing here, so it is going to be 10 ns. Now this one, and what about this one, 1 ns, and this guy 10 gig. So anything when you get into, probably in decimals, or probably zero point 0.1 something like that, always convert it to the next thing. Okay, so it is going to be kind of 100 ps. The clock period is going to be 100 ps, and in this case this is going to be 10 ps. Okay, now let's solve some more problems. Okay, so I want you to, if I give you 2 ns, what is going to be the frequency, and 1.33, what is going to be the frequency. Let's say if I give 800 megahertz, what is the frequency, I mean, clock period. Okay, so 2 ns is basically 500 megahertz. Okay, okay, and 1.33. Okay, so approximately 750 megahertz for the second one, and third one 800 megahertz, it is going to be 1.25 ns. Okay, now Okay, simple thing. Now, this is one of the company which is doing kind of the server chips. Okay, now look at this. So they are supporting say 3 gig frequency. Okay, now what is going to be the clock period? 3 gig clock period. Okay, so Sirisha, you are actually wrong. So 33 NS is wrong answer. Ah, okay. So 330, 330 or 333 PS. Okay. Now, if you guys look at here, say Intel Xeon processor, which is operates at say 3.4 gig. Okay. So now, which so if you look at right, okay, let's take a look at Snapdragon processor. Snapdragon processor. Okay, so if you look at this Snapdragon, what is that they are saying? It is almost like a 2.84 gig. So what is going to be the CPU, the clock uh, period approximately? So the reason is you would know why I'm giving these problems and all through when you go through a couple of classes in my course, because there is something like kind of we would be talking about register to register, okay, paths. Now, so they will have to travel, the data has to travel from here to here within this clock period time, less than one clock period. So you definitely need to have an idea when someone says, okay, I'm working in 3 gig, okay, because I'm working with kind of design with more than 3 gig, okay. So and my clock periods were like kind of 270 PS. You have no idea how much challenges that I am going through. Okay, so you should know how to convert this kind of things on a fraction of seconds. So the moment you see something like this in the written test, you shouldn't even spend time on it. Okay, now uh, so I hope you are able to convert, and now from now onwards, you should be looking at the what do you call, any product that you are trying to buy, you should look at your frequency. Okay, because that is where the performance matter, that's where the performance is. Higher the frequency, your performance would be better, but at the same time you might have to compromise on little power, or the kind of little heat. So it depends. Okay, okay, moving on to the next one. Okay, so I'm sure you guys know, as I told you, like there are things called latch, sequential circuits, and then you have a flip flop. Okay, now when I say latch, What is this meaning? Level sensitive, and whereas flip flop is basically edge triggered. Okay, flip flop meaning it is edge triggered. Now, when I say level sensitive, so you guys know that this is a kind of clock. Okay, so latches would be on during the whole positive edge, or probably say when the latch is or the clock is high, and they would be off during this low time. Okay, the clock signal low time. Now, this is something that we call it level sensitive. So it's basically you open the gate for say for example like this. So 1 minute you close the gate, next 1 minute you open the gate, next 1 minute you close the gate. So you just keep letting whatever that comes in the D, you keep allowing to the queue. So that is what the latch behavior is. Okay. Now, if you look at the way we draw the latch, so sometimes people might get confused, but ideally speaking, your latch will not have the triangle, that edge triggered kind of symbol. So this is, you need to be very careful. This particular triangle kind of thing that I am showing here usually will not be there in the latch. This particular thing, okay. Whereas this case, it is kind of it's purely latch, and this is something that we call it flip flop. So when you say flip flop, it is always you should have it like kind of this triangle. This means it's basically a edge triggered. Okay. Now this is latch. Okay. Now, okay, let's quickly understand the waveforms, how the latch would operate. Okay. You look at here. So this is the clock. Okay. Let me just draw a picture, then we will go with, say for example, this is your clock. Okay. Now say this is your D. Okay. Now, so the first thing is basically you need to do mark these edges. Since it is a latch, so you need to mark both the edges. Okay. Now the next thing is you have to just draw the output. Anything it is there in this window. Okay, anything in this window, you have to just draw it and the output. Okay. Now here, because the window is open during this whole time, and then this is going to be say kind of, see, from here it's going to be going here. Okay. Now whatever that you are drawing it here, no, it have to extend it all the way till here, and from here to here you need to extend it, because this is the place where we call it a storage. When the clock is not active, it stores the lost value. Okay. So this is going to be your output for the latch. Okay. So it's going to be Q latch. Okay. Okay. Can we quickly draw for this? Can we quickly draw for this particular waveforms? Because when I said, set up paper for the hiring, we would be definitely giving some things like this. Okay, so let's quickly take a look at the waveforms. So as I said, exactly the window opens during this passage, the transition, and the window closes at the fall transition, and whatever is there in this active period, when the signal is active, it would be just copied. Okay. Now anything that is there in this, these are all kind of not at all allowed because the signal is clock is not active. Okay, so anything that on the off cycle or during the off state, it will not be propagated or it will not be going through. Now again, the moment it comes over here, so it starts from here to here. Okay, so this is how we say the storage works. So anything on the last, the last state during the clock active, that would be stored or retained till your next edge, next active edge. Okay, so this is the beauty of latch. And if you remember one thing, if you try to recollect, we talked about something called high-end servers in the first class. Something like say IRCTC or Amazon or Flipkart, and they have huge customer base, and you would be getting a lot of during the sale time and everything, right? So Intel, for example, okay, Intel, for example, they try to use latch for their server design. So Intel, if you are trying to get into Intel, you would definitely need to revise your latch based timing analysis. So this is a kind of topic that you should be thorough if you are targeting Intel. Okay. So Intel uses latch a lot. Okay, but all the other companies, they use 95% flip flops. Okay, only 5% they would be using latches. Say for example, you have a design. Say if this is your complete full chip. Okay, now if you go and take the cells, the kind of cells that are being used, the sequentials, so you will see 95% flip-flops and 5% is going to be latches. But in an Intel, it is going to be almost like kind of 95% latches, mainly if you are in the server team, server group. Okay, so if you are targeting Intel server group, it's better you have to be thorough with the latch based timing analysis. I know you guys might not understand what is the meaning of timing analysis and everything, but we will cover that. Uh, But you can go and do your homework if you are planning to target Intel. Okay. So any question on latch? Maybe I'll give you a minute to ask questions. Latch, is that clear? Go. Yes, yes, I can hear you. Go ahead. Yes. No, no. So here, see, it is, see, in this picture, when you are drawing this kind of things, obviously you cannot make it like kind of the transition and all. So it will be tough for you to draw the thing. But now, if you look at the real thing, when in industry, any signal, it is going to be a transition. And remember, say for example, we there is something called buffers. Okay. Now, what is the use of buffer? The transition is something like say like this. Now the buffer is going to be just going to be used. It would be just boosting the signal transition and it would be sending it. So if you look at the before the before the buffer, or say the input, at the input of the buffer, your transition is say kind of 300 ps. Okay. Now the output transition, the transition at the output pin, it is going to be probably see 120 ps. See, like this only your transition would get propagated. Now I cannot put that kind of transition things in this picture, where these are all more of we would definitely ask this kind of questions in interviews, but not in the written tests. Written test, it would be say, it would be tough for you to mark the edges and draw it, whether you need to take it here or take it there. So just learn the concept of what is latch and what is flip flop. That's what I'm looking at. So no, that is what I'm saying. So it is, we will cover everything in a topic called static timing analysis. Okay, so if you look at any kind of sequential elements, they all operate the moment clock comes. So it is always going to be clock to Q delay. We always call it a clock to Q delay. So let it be a latch or let it be a flip flop. Okay, or let it be a macros or say memory. Say you have a memories. Okay, memories are going to be kind of bigger cells, which will have a kind of say address 32, and then you may have a data 16, and there could be many more. So anything, any kind of cells that is getting operated with the clock, they all will have a clock to q delay. Okay. So your propagation delay is there, and those in-depth details we would be covering probably in the coming weeks. So basically, we would look at the transistor level circuit. So in the upcoming week, we would be going through CMOS basics. So why there is a delay, why propagation delay, and how can you reduce the propagation delay, or what are the parameters. So we will be discussing all of them in the upcoming weeks. Okay. Okay. Moving on to the flip flop. So now I want you to take the same clock. Now that is the top one that you whatever that you have. That's nothing but your D. Okay. Now let's draw the output further. So now remember, we always say this is how we mark it. Like kind of the flop is a positive. It's basically a clock signal. This is a kind of positive edge trigger, and this is going to be kind of negative edge trigger. Now take a look at this. Mark your clock edges. Okay, the first thing is basically you're supposed to mark your clock edges, only the positive things, because we are talking about a positive edge triggered flop. Say for example, you just take this as it is, and then it is during this time, it is logic 1. So it is going to be next till here it is going to be logic 1, and during this time it is logic 0. So it is going to be dropping and then it would be continuing. So if you look at only at the time of the clock edge, whatever the value is, that would be considered, nothing else. Okay. See, irrespective of, even in this case, there is a edge is getting changed, and even here the pulse is, the signal is, going high and coming, then, coming to low, and etc. But flip flop behavior is only during the edge, whatever the value, only that would be considered for your waveform, or probably that would be the value it would be coming to your output. Okay, it will not bother any kind of noises coming after that or before that. Okay, so can we quickly draw the waveform for so B, for this B, what is going to be a waveform? So assume this is your clock period, and what is the value? D is basically kind of high. Okay, now it is going to go all the way till next waveform, next clock edge. So here it is low, and it is going to go all the way till your next edge. Say for example, if it is going to go like this, and now this is the time where it is kind of 1, and it is going to go like this. Okay, so your flop output is going to be, say, something like this. Got it? Now the next one is basically negative edge triggered. Okay, now if you look at, this is positive edge triggered flop, and this is negative edge triggered flop. Okay, now if you look at the negative edge triggered, what is that you need to do? Instead of positive edge, you need to start taking your negative edge. Okay, during positive edge, whatever is there, that is not going to be considered. So you have to pick here negative edge. So during negative edge, it is kind of 0, and here it is kind of 1. So the output is going to be kind of, you carry all the way till here, till this edge. So only here it is going to go up. Okay, see here. So, but sometimes what people usually do is, Kumar, I have, this is my the same clock and similar output, but this, can I invert this? So this is my, positive edge trigger, whereas my negative edge trigger, can I just invert it like this? Say for example, say like this, can I invert this output? You are not supposed to do that, because there's a negative edge trigger. But what you are drawing this is something that it is going to be treated as a kind of you adding an inverter here. So you having a negative edge trigger here, and you adding inverter, these two are different circuits. Okay, so you cannot do that. So always, if it is a positive, always take positive. If it is a negative, always take negate circuit. Okay, any questions here? Since, because we are done with this timing diagram thing. So now let me tell you, If you are very strong in this kind of fundamentals, it is going to be very easy for you to get into industry. Yes, these are all the things that people will get confused. Okay, I'll give you a minute to ask questions. Okay, moving on to the next one. Was there any question? Okay, so the next topic, and this is something that important topic. But before that, let me just quickly give you. So you have different flops. Okay, you have different flip flops in the in the textbook that you would have gone through. Say SR flop, and then you have a JK flop, and then you have something called D flop, and then you have something called T flop. Okay, now if you look at in industry, we only use DFF1. We only use DFF. We don't use say SR, JK, and T and all. So the whole industry, all the kind of projects that I have worked all these days, we use only DFF. No other flops would be used in the industry. So you knowing these flops is good to know. It's good, but if you ask me, uh, my suggestion is going to be always focus on the complete D flop. Okay, D and T would help you. Okay, now there is a one more concept that I did not bring it here. So there is something called master slave. So there is something called master slave configuration. So now if you look at, there is something called, okay, why are we coming for, why are we going for master slave? Any specific reason? Why are we going for master slave flops? Any specific reason? You can think your answer. No, no. Exactly, to avoid something called race around condition. So if you go and analyze your JK flops or whatever the flops that you are going to be using, so there is something called race around. Okay, there is something called race around that you would be getting, you would be seeing. So to avoid that, what we are doing is, say for example, you have your kind of the first latch, and then say this is your clock, and I say this is your latch, and I say this is your latch. Okay, so this is going to be your D, and this is going to be your Q. Okay, so the whole thing is what we call it, kind of say master slave, to avoid the race around conditions. These are all small things that we would be asking you in the written tests. So we just give you this kind of thing, and we'll ask you to figure out which is master and which is slave. Okay, and what is the reason behind you coming for this master. Okay, so you should know what is the meaning of master slave, why you are start using master slave, what is the reason behind. So uh, why do you need to have a two latches here? So this is basically a FF flip flop. So okay, so the next question is in terms of area. Okay, in terms of cell area, is latch is less or flip flop is less? So this is a kind of another homework. You can note it down. You might want it to work after the class. So in terms of cell area, which is having lesser area? Is it latch is having a lesser area or flip flop is having a lesser area? Okay. Okay. Moving on to the next one. So excitation table. So any flop that you have studied, right, and all of them would have something called excitation table. Now, what is the meaning of excitation table? It is basically the relationship of your current input and the next input. So basically, what is your next output that you are looking at? Current output and the next output also. So it's like if you look at this is your current output. Okay. Now this is going to be your next output that you would be looking at. Now, if this is the case, what should be your input? So the excitation table tells you that, let's say your current output is zero, say kind of, this is your D flop. Okay, now you have a zero. Now, when you get multiple clock pulses like this, what should be, let's say, what should be your next value? So your next output, you are expecting to be zero. So then you need to keep zero. And let's say you are expecting next output to be 1, so then in that case you need to give input as a 1. So this helps you to design a circuit and what should be your next input and etc. Now ideally speaking, 0 0, so you don't need to worry about, say it's 0. Now 0 and 1, so since it is D flop, you have to give 1 as a input because it is a transparent flop. Okay. Now 1 is there and you want 0, so you have to give 0 as a input, and now you have 1 and you are again looking at 1, so you need to give 1 as a input. Now if you look at, okay, the DR, the input, is supposed to be same as your next stage output. So if you look at the current state not at all matters, because the output, anything that you want, the next stage output, your input has to be same as your next stage. So your D flop, because of this reason only, we call it transparent. Okay, because of this only we call it as a transparent flop. Okay, now let's quickly go over T flop. So what is the meaning of T? It is called toggle. Okay, now take a look at this. Say you have a 0 and you want 0, so that means it's basically you need to give 0. So in this case, when you say 0, 0 means just memory. It's kind of just retains the same value, memory, or we call it retain the same old value, retain old value. Okay, that's called memory. Now when you say 1, it toggles. Okay, what is the meaning of toggle? Toggle meaning if you give 1 at the input, the output would be keep toggling. Okay, say for example, you have a D flop like this. Say here it is 0, the output is 0. Now say for example you give input 0, so basically your T is kind of 0, and when your T is 1, say this is kind of your T input, and this is your say clock. and what is going to be your Q? Since T is and it's 0 at this point of time, and your T is also 0, so the output is going to be in 0 as long as the T is 0. Now this is your time where your T is 1. Now 0 becomes 1. Okay, now it continues all the way till your next thing. Now what is that? T is 1 and your output is going to go to logic low. So your output, the output level would be keep toggling. Okay, so that is the beauty of the toggle flop. So when your T is 1, okay, your output keep changing its state every clock cycle. Okay, that is the meaning of your T flop. Okay, now take a look at this. So when what did I say? If you are expecting it to be kind of retain the same value, so you can say kind of 0. Now see 0 is here, but you want 1, so you need to keep this as a 1 because so that it will toggle. Now so you have 1 and you want the next state to be kind of 0, and this again what is that? It's changing the state, so you need to keep 1 as a toggling, so that if you keep 1 then only the output would be toggled. Now these two again it's the same state, so you can keep 0. So these two flops, if you know, probably this is good enough. Okay, you don't need to worry about anything extra beyond this. So see, sometimes why I'm covering this whole digital part, because sometimes, say for example, companies like, so though you are doing PD course, okay, but sometimes companies like Intel, okay, or say AMD, Nvidia, okay, the interviewer might be coming from a different domain. Remember, so if you are going through a regular, hire referral or probably the hiring process, so they, I told you guys, right? So you will be going through, resume shortlisting and written test and all of that. So the person who's going to interview you may not be from PD, may or may not be from PD. Okay, so in case if he comes from say kind of the design background, okay, so the digital design background, okay, now you knowing all this makes life easier for you, because let's say if they have to interview 100 people and they will not find all the 100 PD engineers to interview. Okay, so maybe some front end guys or some verification guys or some other guys, department guys or domain guys would come and help the hiring. So if they are not from PD background, is you having a PD skills is a good thing, but in interview you might have a tough time. Okay, or probably you passing that round is going to be a little tough. So you, let's say at that time, if you know, if you are good in digital, if you are good in digital and CMOS, probably you would be able to clear, because the digital and CMOS is basic for anyone. Okay, so you can take that all the question, we can tell them. Maybe if they would definitely ask you what is your strong domain, is it like which is your strong subject, or which is your in which domain you are expert. So you can say digital design or say PD or STA or something. So you should know what kind of flops and how the flops operates. So let's say now, how did I explain this? So the way you, I mean, I explained, you should be able to explain the similar way, then you would be able to get shortlisted. Let me tell you, though I am a PD manager, okay, but I do go for campus hiring where they might have not learned PD. So I have to judge them based on their digital circuits and some basic say kind of microprocessors, or since basic KCL, KVL. So you should look at from that angle. It's not about you go whether it is needed for you, for the PD engineer or not, but many entry level guys, would go through different, the interviewer will come from different, domain. That is the main reason I'm trying to cover. And you knowing them is also an important for a PD engineer. Okay. So don't think that, okay, PD and is just covering, all the basics that I gone through. I'm just refreshing your knowledge. Okay, so we would be using these excitation table when we design the circuits. Okay, in the next slide, a couple of more slides, uh, we will try to, design a circuit. Okay, using these excitation tables. Okay, now any question on this excitation table before we move to something called registers? No questions. Okay, moving on to the shift registers. Basically registers. Okay, so what is a register? So it's basically register is a storage element which stores the value. So remember, in industry we always call flip flop also registers. Okay, so if you look at anything that I draw, we always call it like kind of reg to reg paths. So this is register. Say this is register. So we call this as a reg to reg paths. Okay, and say let's say this is your input. Now this is going to be kind of into reg, and say this is going to be, say assume this is your output, so it's going to be into reg this is, and this is going to be reg to out. So you going through this particular topic at this point of time will probably help you to understand what is the meaning of into reg paths and reg to reg paths and reg to out paths. Okay, so people would actually in industry call registers, meaning it is a one bit flop. One bit flop also known as, we call it as a register. Okay, now moving on to our actual topic, so register. So registers are basically used to store the values. Okay, now if you look at, there are different types of registers. Okay, so what are the different types of registers? So now let's take a look at it. So this is what kind of register, can someone tell me quickly? What kind of register is this? So this is basically each and every flop that is basically loaded. The values are loaded, individually, and they do have the output, and or probably they send out the output in parallel. Now, why do you need these registers? Because anyway they are kind of, just storing the value. But why you need the registers? Why do you need these registers? So you can directly use, I3. You can give it to I3 directly to Q3. No, remember, why do we need is, say for example, say you have a ALU. Say you have a ALU. Okay, now it has to calculate some things. So say this is A 4 bit, and say this is kind of B, this kind of 4 bit. Now your output, okay, say this may be 8 bit or something like that. Okay, now if the inputs are keep on changing, then this ALU will not be able to give you the output. Okay, now so to avoid that, now if you clocked it through, so we call it clocking these values, clocking these signals. If you send them through a register, now these are going to be constant till your next clock pulse comes. So what we do is basically, when you are ready, when the computation is out, say after some kind of say 1 ns. By the 1 ns time, your output should have been available. So you can just always put like kind of your clock pulse as a 1 ns, so that like your ALU have enough time to compute and send the signal out. Okay. Now say simple, right? Say for example, now you just say 1011 and say 0101. Okay. Now you have to add these two numbers. Okay. Now the whole addition, the amount of time that you are giving, say 1 ns. Okay. So the moment you load your signal and it goes through your ALU, and it gets added and all the kind of process it is done, and this is going to be kind of available, okay, at the flop. And this would be again clocked. Okay, this would be again clocked at the, say they add another 4 or 8 flops are called registers, and then they send it out. Now that means every 1 ns you keep getting a value, every 1 ns you keep getting a value. So this is how all the kind of circuits that are being designed in the industry. So basically you need, see, everyone is basically struggling with the moving data or probably constantly changing data. So any kind of operations that you wanted to do, that the data should be stable. You cannot do any kind of operation on a constantly changing data. Okay. So metastable, I want you guys to go and read about something called metastable. Okay, you can just write down this particular keyword, metastable. You can go and brush up through, then you can come. Now, so you need shift registers, or basically your registers, to make sure your data is constant when there is some kind of operation that is being done. So for that purpose only we use all these registers. Okay, any questions? Okay, go ahead, go ahead. Which one? Okay, I'll come to that. I have not started any of this. I'm just trying to make you guys understand why you need registers in the design first of all. See, you might have gone through in colleges register as a topic, but where it is used and why you need them, I'm just trying to give you the practical side of it. So when I say ALU, it can do any kind of operation, say addition, subtraction, multiplication, and etc. So when your ALU is is performing that operation, your data has to be constant. So now how can you ensure that a constant data? You have to send it through a register, control it with the clock. Okay. Now moving on to the next certain things called shift register. Say for example, it's basically a group of flip flops connected in a chain. So this is actually kind of what is a this kind of parallel in, parallel out, but you do have a different types of registers. Say, for example, you have a serial in, serial out, parallel in, serial out, and serial in and parallel out. Now, if you look at these two kind of registers would be used. Say, for example, you have a transmitter here. Okay, it is passing the data through a single medium. Say, kind of one bit, or you may have a kind of wire or something. So your receiver. Now what is that we do here? Probably you would use this as a kind of serial out. So you would pick something called serial out, in this case serial out. Okay, now this guy you will have to pick serial in. Okay, it can be serial in, serial out, or parallel in, serial out, but this guy can be serial in, parallel out, or serial in, serial out. So any kind of system that is sending a data through a medium, or say kind of single wire, or kind of lesser number of bits and etc. So we use serial out and serial in kind of the thing, and then we take the data out. Okay, so if you understand, there will be a kind of designs where your phi layer, it's like say DDR IP. Okay, you will have a certain phi which would be operate working, or behaving as a transmitter, and there will be a set of DDR IPs working as a receiver. Okay, so during that time, this kind of configurations people would be using it. Okay, so parallel and parallel out would be used in kind of in case of the CPU or some other things where they want the data to be constant when or while the ALU is processing them. Okay, now if you look at what is serial in, serial out, so basically a group of flops connected in a chain, so that's called, we call it a register. It's basically a registers. Now how you connect them is what differentiates, or that's how we call name them. Okay, say serial in, serial out, and parallel in, serial out. Okay, let's take a quick look at say data input. Okay, this is serial in, this is serial out, and again serial in. It's kind of serial out, serial in. So now this is something we call say serial in and serial out. Okay, because you just keep giving data only one bit at a time. Okay, now when you say parallel and serial out, what does this meaning is, so each and every flop will have kind of say a logic here. Say a logic here. Now all those logics, so when you say a load signal, or say something like this, load is active, anything that you give, say D0, D1, say D2 or D3. Now during one shot all would be loaded, but when the load is zero, this queue would be shifted here, this queue would be shifted here, the queue would be shifted here. So this is something that we call it a parallel in, okay, and serial out. So basically what you do is you load everything in one cycle. Okay, now you have all of them to get all of them out. How many cycles you need? Can you guys tell me? So let's say I'm trying to load 1011. Now how many cycle I need to get this out? Can you tell me? 1011 is my, sorry, okay, 1101. So now how many cycles I need to get the whole data out? Can you guys tell me? Because it is a 4 bit, you need 4 cycles. Okay, so you need basically 4 cycles to get all the data, empty the whole set of registers. Okay, now this is something that we call it a parallel and serial out. Any question? And moving on to the next one, you can ask your question or you can type your question in. Okay, next is basically serial and parallel out. What is this meaning? This meaning is going to be, so you just keep sending the data here. So this is going to be say kind of Q3, say Q2, Q1. So it's basically like this. So you will have it like kind of some combo logic, which is going to be when the transfer is happening, you will have it like kind of Q0, say something like this. So now input would be coming in, and all the flops would be loaded one after other, and then you would just send it out in one shot. You send all the four. So again, four cycle you load, and then it's something like you send all of them out. Okay. So there is something like serial and parallel out, and parallel out we just saw it. Now, what is this universal shift registers? Okay, so universal shift register. So this is something that you would see. Say for example, you have a control signals. Okay, so you design a system. Okay, say you have a signal, or say system. Say you have a 4-bit A. Okay, input, and then you do have a two control signal S1 and S0, and say you have a Q. Okay, now say S1, S0, 0, just pure register, just parallel and parallel load kind of thing. 0 and 1. Now shift left. Okay, now 1 0, all the data would be shift right. Okay, and 1 1, see, kind of any other operation. So you will have something like universal shift registers where the CPU will have something like this, because if you guys try to recollect binary additions or binary operations, so you will have something like 1 1, and you invert it like kind of 0 1 0 0, and add one thing once complement, and then add one, some things like that, and all you would do. So during that time, you having this universal shift register, or say you can say during this time, so invert of all the data, so all data would be kind of say inverted. Okay, so depending on the control signal, the universal shift registers, okay, you would be able to design whatever the operation that you wanted to carry out. So maybe you guys can go back and give a try, design a universal shift registers where 0 0 it just a kind of normally sends out the data, and in case of 0 and 1, so it is going to be first side, say kind of, if this is your 0, so your input, now shift left. Okay, so it is going to be 0 1 1 0, something like this. Okay, or shift right, so 0 1 0 1, something like this. So you can, so this is the time where you can actually go and practice. Okay, once we start your PD topics, I can bet you will not have time. I'll not give you time to do any of this. So go and learn the digital fundamentals. I mean, the all small problems, and learn your probably the design skills. Okay. So universal shift register, that is actually we have a lot of we use this a lot in our regular designs. Okay, so though you will not directly call it as a universal shift register, by looking at the design, you would be able to tell that okay, yeah, I'm this kind of universal registers. Okay. So any questions on this slide? I'm done with this slide and the whole topic of say excitation table and registers and etc. No questions? Okay. Okay, so we have a few more slides. By 11:30 we should be able to finish it. Okay. So the next topic is basically counters. So why do you need counters? Why do you need counters? Okay, a simple thing, no? Okay. You take your regular watch, time time watch. Okay. So how is the time? What is the kind of the how it is gives you output? Say XX hours, YY minutes, and ZZ seconds. Correct. Now, So when you increase your minute, can you tell me when you increase your minute? After 60 seconds, correct? 1 minute. Okay, 0 to 59, and then it turns out to be again 0, and this is actually going to be increasing by 1. Right now, when your minute becomes say 59, what happens? Your hour is getting increased by 1. Now, what is this meaning? You will have your thing, it's like kind of say 12, okay, and then 59, and then 59. So this is a kind of maximum number that you would be looking at in case of a say a clock, right? Now, how do you design this in a circuit? How do you design this in a circuit? So now it keeps increasing, right? One after other, one after other, one after other, and then the moment you hit the threshold, it gets reset, and then this actually incremented. Correct. Now, in this kind of scenarios, you have to use counters. Okay, a simple thing. Now, assume you are in a factory. Okay, you are kind of packing. You are kind of packing something in the say for example you say for example take a Pepsi. Okay, so they pack a cotton box. So they say a kind of 5 bottles. Okay, so every 5 bottles they so in each and every bag cotton box, say 5 bottles can they are filling. Okay, now after 5 bottles dropped, okay, the cotton has to move, the new cotton has to come in. Okay, so this is the kind of automation or probably the places that is being used. So you need to keep counting the elements or probably say objects, and once it is done, say once it reaches the threshold limit, you create a kind of control signal which would go on to the next set of process. Say in this case you filled this first one, two, three, four, five. Now this has to move here, okay, for taping completely, tape it and close and send it. Now when it is moving, the next cotton box has to come in here, and it starts next 5 bottles. Now again after 5 bottles this has to keep moving. So these are all the kind of places, the real-time examples that you can think of when it comes to counter. Okay. So let's quickly take a look at it. So probably you can go and start working on a small projects like a digital timer, design a digital timer. So the people who are in kind of say third year or final year, you take this as a small project, design a digital timer. Okay, it can be using a say kind of Verilog. Okay, or you can try direct hardware on your paper and etc. So you learning something like this is no harm. It's going to improve your overall knowledge. Okay, so digital timer you can give a try. Okay, let's talk about the counters. Say for example now say 000. Okay, now this is your say current state. Now you get a pulse. Now what is that going to be next? Say one pulse, your 0 0 would become a next one. So 0 0 1. Okay, so 0 1 0. So that is your current state. If it is your counter is in 0. Okay, now you get some kind of inputs. Your counter is going to show say 1, next 2, something like this. So that means if your counter is in state of 0, after say input, it would go to next one, say 0, 1. Now if it is already in 1, then it would go to the next one. So this is how a system is being designed. So when you're designing a system, you know your present state. Say, for example, this is the kind of value. Now, if I get an input, certain input, this is going to be my next value. So you have a complete control. Okay. Now, say if this is my state, the next thing is going to be this. So that is how you design a complete system. Okay. So counters can act as a simple clocks to keep a track of, say, time or say any kind of count and etc. Now, modulus is 2 and where n is the number of flops. So that means if you look at, so you have a 4 flops in this case. So now how much, how many states you can count using these 4 flops? 2 to the power n. Okay, so that means 0 to 15 you can count. Now let's say you have a 3 flops. So only 3 flops. Now how many states that you would be able to count? How many states you would be able to count? It is going to be say 0 to 7. So basically 8 states. So 0 to 7. Okay. Now when we are designing a counter in textbooks, you would have probably used completely the T flip flop. Okay. And you can stick with that, but also remember, you can also try design a counter using D flops also, using D flops. Okay. Now moving back to the regular topic. So you guys would have heard about something called synchronous circuit. Do you know what is synchronous and what is asynchronous? And I have to talk about something called setup and hold also. Okay, we will cover that after the slide. So what is synchronous and what is the meaning of asynchronous? Okay, so synchronous meaning, so look at this, all the registers are clocked by a signal called clock or operated by a signal called clock. Okay, so the clock would reach all the registers at the same time. Okay, now what is the meaning of asynchronous? Asynchronous meaning, say you have a register and there is another register and there is another register. Now in case of synchronous, all of them would be connected to the same clock. Okay, but in case of asynchronous, this output going to be treated as a clock for the next state. Okay, so this is something that we call it asynchronous. Okay, now if you look at asynchronous, we don't use, or probably we don't follow this asynchronous circuits. Okay, the whole industry actually follows only synchronous circuits. Okay, synchronous type. Okay, now remember we talked about 3 gig speed. What is this meaning? Your clock period is triple three PS. Okay, now so you can ensure the data operation between these two this can be within 333 PS. But in case of this, you have no idea how much time it is going to take. So something like STA, static timing analysis, is supporting only kind of synchronous circuits. For asynchronous, we don't have a kind of methodology to say this will work at 3 gig. We cannot say that this will work at 3 gig. We don't have any kind of mechanism to validate it. So for the asynchronous circuit, so anything that you talk about static timing analysis, okay, you can just go and note it, just take a look at it, what is STA and etc. Okay, so asynchronous circuits, we cannot confirm or probably do the timing sign off. Okay, say for example whatever the frequency that you are targeting. So only synchronous circuits we can easily go and implement and make sure you can verify and make sure your design is going to operate at 3 gig, say something like that. Okay. So in industry we use almost 99.9% synchronous circuits. And you might ask me, Kumar, what happened to that the 0.01%? There are some companies who are still trying to see if this asynchronous is going to work, but I have never seen any product with asynchronous styles. Okay. Okay. Can we quickly design a counter and then we will drop for the day? So this is going to be your next state, and this is going to be your inputs. Okay, so next state input supposed to be. Now, if you look at this, the whole thing, okay, 000. Now this 00, the whole thing is basically convert becomes one after your first input, first pulse. Okay, and then if it is one, it becomes, so basically let's do this. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, so this is your decimal number. Okay, okay. Now this 00 becomes, this is your current state, and this is going to be your next state. Okay, now you need to pick this, say 0 becomes 1. So what are we going to do here? We are going to design this as counter using T flop. Okay, now, so the whole thing, right, 0 to 1, you know what is that you need to keep? You need to keep, okay, let me just keep that excitation table side by so that you guys can easily understand. Now take a look at this. So from 1 to 0, 0 to 1, so the whole thing is going to be kind of, you need to give the T, first T flop is going to be treated as a 1 always. Okay. Now the next one here, look at this 0 0. So refer this particular, okay, 0 0. What is that? It is going to be, see, 0. Okay, and 0 to 1 it is going to be 1, and 1 to 1 it is going to be 0, 1 to 0 it is going to be 1. Now 0 to 0 0, and 0 to 1 and it is going to be 1, and 1 to 1 it is going to be 0, and this is going to be 1. Okay, and so here 1. Okay, so this we are done, and the next one, so these are all three zeros and three zeros are here, so it is going to be kind of, see, 0 0 0. Look, I'm just filling based on, see, when I'm filling this web data, this is going to be my, say, uh, the T0. Okay, so this is going to be my T1, and this is going to be my T2. Okay, this is going to be my Q0, this is going to be my Q1, and this is going to be my Q2. Okay, now this is going to be the next state. Okay, basically, so plus next state. Okay, plus 1, plus 1, and plus 1. Okay, now consider this, now 1 here, you have a q2 0, and you want the q2 to be next, which state next is going to be 1, so you have to fill this as a 1. Now look at this, here it is 1, and here it is, these three are 1, so you have to, it's a memory, no, 1 to 1 it is equal to, you look at this, if it is 1 and you want next state also to be 1, and your input should be kind of 0. So 3 is going to be 0, and then finally 1, and you want next state to be 0. Now this is going to be 1. Okay. Now what is that you have to do here? You have to solve these equations, right? Solve this particular thing. Now follow the Karnaugh map, simple Karnaugh map. Okay. So if you try to follow the Karnaugh map, simple Karnaugh map, it is going to be kind of, say, all of them are 1. Say in terms of T0, all of them are kind of, say, 1. Okay, and you get a maximum coverage of all of them, and your T0 has to be 1 always. Okay, because you, when you group all of them, the output is going to be 1. Okay, now the next one, so this is going to be kind of, say, guys, can you please go on mute? So this is going to be Q2, Q1, and Q0. Okay, so Q2, Q1, Q0. Now, so 1 here, so it's 3 is going to be 1, and 5 is going to be 1 here, and 7 is going to be 1 here. Okay, now what is this meaning here? This is going to be, so this Q2 is not going to be there, and so 0 0 0 1 1 and 1 0. So now what is it going to be here? Q0. So T1 is equal to Q0. Okay, and here T2, what is it going to be the Karnaugh map? Q2, Q1, Q0. Now take a look at it. Now, so 3 and then 7. So you know that only these two are going to be the case. So now this is going to be Q1 and Q0. So your T2 is going to be Q1 into Q0. Now you have got the whole thing. Now what is going to be the circuit? So your circuit is going to be say like this. So now this is going to be your T0, T1 and T2. Okay. Now T0 is going to be always connected to 1 because that is what we have derived. Okay. Now T1 is basically just a same Q0. It is given to the T1. Okay. And the second one T2 is going to be AND of Q1 and Q0. Okay. So what is this meaning? Okay, so this is how you design a kind of mod 8 counter. Okay, so this is how you design a mod 8 counter. Any questions? So first you need to write your table, state tables, present state, next state, and your inputs. Okay, and you need to use your excitation table and fill these inputs. What is the right set of inputs that you have to target? Then solve them using this Karnaugh maps, and then figure out what is going to be the equation for your inputs. Okay, and then finally you draw this circuit. All are there in front of you. Just have to you need to apply the concept of how to design. What is the step, each step. Okay. Any question on this counters? Okay, all right. uh, okay, so you guys can try these things in home. Okay, you guys can try these things in your home in the upcoming week. So synchronous counters and what is the meaning of ripple counter and decade counter, ring counter and Johnson counter. Just understand what is what, and you can also try designing a mod 6 counter or mod 12 and mod 15 using different flip flops. Okay, uh, and for your homework for the next week, what is setup time? What is setup time and what is hold time? Okay, and what will happen when you violate them? Okay, what will happen when you violate setup and hold? When you violate setup and hold. Okay, and try to understand the basics of four types of paths. Four types of paths. Okay, what is that? Into rich, reg to reg, and reg to out, and in to out. Okay, So these are all some things that probably I want you to look into it, okay, before you come to the next class. And so the next few slides are going to be basics of FSM, and uh, we may not even cover that much because these are all meant for the digital designers. But we'll just quickly go over and just spend say maybe 10-15 minutes, not more than that. Okay, and then after, the next class is going to be. So in the next class, probably we will just quickly go through basics of CMOS. Okay, so MOSFETs operations, and then what are the second order effects, and then you will have CMOS inverter basics and NAND, NOR, and how do you design a circuit for a given Boolean equations. Okay, something like this, and then we will also try to understand the layers in VLSI, and then we will also try to understand something called layout design. Okay, so the whole thing we will go through in the next subsequent classes. So when we finish the whole slides, this would be the end of the CMOS circuits as well. So basically, the digital and the CMOS would be get over probably in a day, in another 2 to 3 weeks time. Okay.